So now in this video, we're going to look at a comparator circuit using the LM393, which can't tell if you can read that or not, but it says LM393N, or we could just call it the 393 comparator. So it is actually a dual comparator. There is one on this side here, these top 3 pins, and then one on this side, these bottom 3 pins right there. We have to power the integrated circuit, of course, and generally all integrated circuits, or all the ones I got anyways, you got to power them and to do what they do. So now we are going to power it with a low voltage power supply. So that's the nice thing about this one. It has an open collector output, and so because of that it doesn't need much voltage, and we can get the rail voltages pretty easy, but there's a special way to do that. So we're only going to deal with 2.2 volts, and that is a single supply right here, positive and negative. The data sheet says it can go down to 2 volts, but I find with this particular circuit I need 2.2 volts. So in any case, let's get to it. The output does not output a high signal because it's an open collector. And so when you see open collector, that's what it means. We actually need a resistor. So this is a 1 kilo ohm resistor. We're going to put it to the output. That is the top pin, the output. The pin below it is the inverting input. When you're looking at schematics, that will be the negative symbol. And so negative symbol is inverting. The positive symbol is non-inverting. And so non-inverting means the output is going to be like the non-inverting input. When it is higher than the inverting input, then the output is going to be high. When the voltage at the non-inverting input is lower than the inverting input, then the output will be low. And actually, when it is low, that just means the output pin connects directly to ground. And then when the output is high, basically it's like a switch that's turned off, and the voltage is provided by this resistor. And I'm using a 1 kilo ohm resistor because we don't need much current. We're dealing with low voltages. We're going to be lighting an LED. So actually we are going to need to amplify the signal. So I have here a NPN bipolar junction transistor. This is the 2N2222, and then it's the A version, but any 2N2222 in the TO92 package will work. And so the left pin's the emitter, middle pin is the base, right pin is the collector. So we're going to put the base to this jumper that goes to the output, the top pin right there on the left, pin number 1. And down here we have the emitter going directly to ground. That's we're going to use it as a switch, and so the emitter just goes directly to ground. That will allow us to have a positive signal come through the resistor, and then when that is turned off basically, but that means we have a high output, that will go to the base. There'll be a diode drop and it will go to ground. We'll have a path there. When the output is low though, whatever comes here will go directly to ground, and it will not influence the switch. And so the switch will be either on or off, and we're going to light an LED. So the cathode, the short lead, goes to the collector right there, and the long lead, the anode, goes up 1 row. Now we're going to take a 100 ohm resistor. It doesn't need to be this high because we're only dealing with a little more than 2 volts, and this is going to drop almost 2 volts. So we're dealing with very low currents in this circuit, but this is just really a demonstration circuit. So plug that to the positive rail, and then to right next to where the anode is, right there. So there you can see that. And so yeah, we could use a lower value resistor perfectly fine. I'm not sure the lowest value, but in any case this will work fine. Now our output's done. That is our load. We are going to have to give our signals to the inverting input and the non-inverting input. So first, let's give the voltage to the inverting input right there. And so we got that resistor directly to the positive rail. It's a 10 kilo ohm resistor. Value doesn't matter, but for this particular circuit we're using the same value resistor. So 10 kilo ohm there, 10 kilo ohm there. That is a voltage divider. And hopefully you already know about voltage dividers. If you have a point where the one resistor of a certain value goes to the positive rail and the same value resistor goes to the negative rail, where they connect there will be half of the power supply voltage. Now, the other input, the non-inverting input, we're going to control with the trim pot here. And so, as I said before, when I'm going to turn this down, so that's less than halfway, and then that means it will be lower than what we have here. So the output will be low. And when we turn it more than halfway, then we'll have a higher voltage. Because again, it's a voltage divider just like these, but it's adjustable. You can change the resistance. So now there's less resistance towards the positive side. It's going to have higher than half of the power supply voltage. Now there's less resistance towards the negative side. It's going to have a lower voltage than half of the voltage, power supply voltage that we set there. We're just going to take a green jumper and make that connection right there and bring that to the non-inverting input. So basically the output is going to shadow what the non-inverting input voltage is compared to the inverting voltage, but it's going to saturate. We're going to get the rail voltage either high because of the resistor or low because it's connected directly to ground. Now the power is not being provided to the rail yet because it's off there. I have to hit the power switch right there, and the output goes on. So the trim pot is turned towards the negative rail right there, and we can see that a little current is flowing. Current is always going to flow in this particular circuit because we have this resistor here, current's going through the resistor. Now it's being sucked to ground because the trim pot is more negative than halfway. So let's turn it till it's more positive, and now we need the current to light the LED that's going through the current's going through that resistor through a diode drop, so we still have that current just slightly lower. And we also have the switch here, the transistor switch is on now, and so the LED is on, but the output is high. That gets the transistor conducting as a switch, and there we go lower. So the data sheet says this can go down to 2 volts, this integrated circuit. And so let's try going down to 2. We'll go to 2. There's a down arrow here. We'll go to 2.1. Now you see the LED is off, and I can't do anything. So for this particular circuit, we can't go down that low. There we go. But we can go higher, and mostly it's determined by, you can see the current's going up too, by the resistor we're using here. So I think this may still be good for 3.3 or so volts. I'm not sure, but in any case, we can go up a bit higher, but ultimately the resistor protecting the LED is more important at higher voltages. It has to be able to handle the wattage and limit the current through the LED. Luckily, we can get a sense of the current going through the LED by looking at this. So now there's probably a milliamp or 2 going through this resistor to get the transistor going, and then probably about 13, I'm guessing, milliamps of current going through that resistor and that LED, so we can lower the voltage. But in any case, pretty simple circuit really. It's a comparator. The only thing is we have the open collector output, which is a little different when it comes to there, but we do have an actual 0 volts when we have the transistor, or the comparator. When the comparator output is low, it goes all the way to the negative rail, and that is a challenge sometimes with comparators and op amps and whatnot. So we can go to 0, so we can use a single supply, and as you can see, we can use a low voltage single supply pretty effectively. We do have to use a transistor for the output because we have quite a bit of resistance here, but in any case, it works just fine. So hope you enjoyed the video. Thanks for watching. I will see you in the next video.